models. That's it. The issue with best subset selection was 2 to the p and the fact that that number can be really large. In forward stepwise, we're kind of doing some sort of local search instead of some global search. So let me first draw a plot of these different models that we are comparing. So with best subset selection, we had 32 models. So here, this plot, this is a plot of R squared based on number of predictors. And all those 32 models are going to be represented here. So the model that doesn't have any predictors, M0, ends up in here because R squared of a model without a predictor will be 0. Then when we have one predictor, there are 5 possible models. So maybe one of them has this much R squared, another one a bit higher, and so on. So these are, let's say, those 5 models with one predictor. These 5 models are these 5 models. All of them have one predictor, and for comparing them, we can just compare vertically on this plot and say that this is the suitable model. Then with 2 predictors, you know, the worst thing that can happen is, I guess, something like this. So there are actually 10 possible models. So there will be some, you know, some of them overlapping, but there are 10 of them here. And again, between these 10 models, this is the best model. Then when p is 3, again, there are 10 models. They have, you know, different values of R squared, and this is the best one. With 4 predictors, there are going to be 5 models. So there are 5 points on this plot. And with 5 predictors, maybe we are here. So let's say this is 1, because R squared cannot exceed 1. So in step 2 of this process, we were making these sort of comparisons. And this is essentially M0. This one here is M1. This one is M2. This is M3. This is M4. And this is M5. And in step 3, essentially we need to make a decision between these 6 data points. And the decision is not as simple as saying, well, this plot is increasing, let's just pick this. Because as I said, this plot has to be monotonically increasing. And for making a decision between M5, M4, M3, M2, M1, and M0, we need to use cross-validation. All right, so in here we have 32 points, so 32 models, and that was the issue. Now with forward stepwise selection, this is the plot that we would get. 1, 5, 0, and 0. So again, we have M0 in here. So we start with a model that doesn't have any predictors. And then in the next step, we're going to try the 5 possible models with one predictor. Maybe here. Those 5 models will be, let's say, these ones. And again, this will be M1. So up to here, I guess everything is similar to best subset. But in the second step, we're going to try only 4 other models, not 10 other models, because we're going to just pick this M1. We pick M1, and then we augment it with 1 additional predictor. Therefore, what we're going to get is either this, or this, or this, or this. So we have only 4 points instead of 10 points. And then the best of these, we call it M2. M2 in here doesn't necessarily match with M2 from best subset selection. Then for 3, now we have the model with 2 predictors. We call it M2. Now we're going to augment it by adding 1 more predictor to M2. So how many different ways can we do that? Well, we have already selected 2 predictors. There are 3 other predictors to choose from. So there are only 3 possibilities. So one of them will be here, one of them here, let's say one of them here. So we pick this, we call it M3. In the next step, there are 2 remaining predictors. And we add, you know, one of them to M3 that gives us the highest R squared. So let's say it will be this one. And then in the next step, there's only one possibility. There will be some M5. So with this sort of local optimization approach, we're going to get another curve. And again, for making a decision between M0, M1, M2, M3, M4, M5, we use cross-validation. So just to repeat, we start in step 1. We start with a model with no predictors, which is M0. Then for, let's say, for k equal 1 all the way to p minus k, we augment mk with one additional predictor So here we had m0, and then we augment it to this, 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 and this, and this. There are 5 possibilities to make this model a bit larger. Then we pick mk plus 1 as the best model with k plus 1 predictors. After step 2, we're going to have m0, m1, all the way to mp. And there's going to be a step 3 similar to step 3 from best subset selection. So we use a cross-validation procedure to pick the single best model out of these. So again, in soft cross-validation, there are a couple of other alternatives. CP, AIC, BIC, and adjusted R squared, but cross-validation is our preferred method because it doesn't have any limitation. Each of these methods has some limitations. So this is forward stepwise, and the plot that we would get starts from the same place, similar to best subset selection. So if best subset selection ends up here, maybe with forward stepwise selection, maybe we end up here. Forward stepwise. This is because in here we're doing some sort of local optimization, in here we're doing global optimization. This is more costly and this is more computationally efficient. So you might be wondering how many models are we comparing? So let's see. Number of models that we are comparing, I can see it here. I have 1 and then 5 and 4, 3, 2, and 1 again. So the number of models are 1 in here, and then it's 5. 5 is p, because we had 5 columns in our data set, and then p minus 1 all the way, p minus 2, p minus 3, all the way to 1 again. So this is equal to 1 plus the numbers 1 all the way to p, which is p times p plus 1 divided by 2. So this is roughly equal to p squared. So the computational advantage of this method is that instead of dealing with 2 to the power of p, we're dealing with p to the power of 2. So in the case of 40 predictors, that method gives us 2 to the 40 possible models that we need to explore and choose from. Here, this one is going to give us 40 to the power of 2, which is still manageable, right? It will be 1,600 compared to that huge number that I wrote. Any questions? No? Any questions? No? Yep. So one thing about this plot is that as these models are nested, we cannot get any worse than the previous one. So these models are nested. And that's why we don't necessarily end up in the globally optimal solution to that model selection process. So here with best subset selection, the globally optimal solution could be something like this. A model with, let's say, these 3 predictors. So there's an example in your textbook, and let's say the best model for making a prediction in the credit data set is using limit, using credit score, and let's say whether someone is a student or not. So these are the 3, predictors for predicting balance. So this is the globally optimal solution. And the way that we get this is perhaps, here we start with no predictors. Then maybe the best univariate model, let's say, is going to have limit. Then the next one is going to have limit and income. Then the third one is going to be the model without income and with score and student. So here, as we are exploring globally, anything can happen. From M2 to M3, we may remove some variables and include some other variables. We don't have any restriction. But the same data set with forward stepwise selection, we may end up with, let's say, limit, income, and student. The reason is here M1 becomes the model that has limit as the predictor. Then M2 becomes a model with with limit and income. Then in M3 we cannot get rid of income anymore because these models are nested. So M3 is going to be same as M2 plus one additional variable. Therefore, maybe because of collinearity between variables, maybe it is ideal between M2 and M3 to get rid of income and include score and student. But with forward stepwise method, we cannot get rid of income, so it stays in the model, and that's why our model is not going to be as good as the model we would get from best subset selection. So this is because of collinearity between variables. Otherwise, if we are running these models on data where columns are independent from each other, don't have any correlation, the result of these two models are going to match. This is if we are running these models on principal components of these features, because principal components are independent. They are orthogonal to each other. Any questions? All right, so we covered forward stepwise selection. There's also a backward stepwise selection. So backward stepwise selection. So with backward stepwise selection, we're doing something similar to this, but we start from the right. So we need to start with M sub P. So we start with the model that has all the predictors, then we do some sort of local optimization, but in a backward way. So in the next step, we're going to remove one of these predictors that has the least detrimental effect on the fitness of the model. So from M5, it has 5 predictors, therefore we need to select 1 out of 5 possible predictors to remove, and that's going to give us, let's say, 5 different models with 4 predictors. Right? In one of them we remove feature 1, in the other we remove feature 2, feature 3, 4, and 5. That's how we get 5 models with 4 predictors in each. Then we just continue this process. Now between these models, we're going to pick the best of them. So the best model is this one. That was when we remove something, we remove the features, we made the model sparser without sacrificing too much on the fitness, too much on R squared. So this becomes M4. Now that we have M4, we're going to remove one more predictor. That would be 1 out of 4. So there are 4 possibilities. Therefore, we get, let's say, these 4 models. Between these 4 models, this one is now M3 because vertically we can just compare them based on R squared and say this one is better in terms of fitness. These are comparing oranges to oranges. This is fine. But making comparison between these models, we cannot use R squared. We need to use cross-validation. Then in the next step, so these are models with 3 predictors. There are 3 ways that we can make them even sparser, and that gives us these 3 models. This one is the best model with 2 predictors based on this local search. So this is M2. Then there are 2 different ways to make it a univariate regression model. There are 2 predictors. We can get rid of the first one or get rid of the second one. And that gives us, let's say, these 2 models. This one is better in terms of fitness. We call it M1. And then M0 is the same as M0 everywhere else. It's just a model with no predictor. So this method is going to give us a different curve, a different set of M0 to M5. So just to update the method for backward stepwise, we're going to start with M5 or MP. Then for k equals p minus 1 all the way to 1, we're going to remove one predictor we're going to remove one predictor from mk. Then we pick mk minus 1 as the best model with k minus 1 predictors. That's just the vertical comparison between these models. That gives us a set of these models, m0 to mp, and then we pick a single best model using cross-validation, and that's the process for backward stepwise selection. So you also have access to this on the lecture slides on Quarkus. Exactly the same process. Any questions?
It's the same number of models that's sorted, right?
Sorry?
It's the same number of models that's sorted, right?
Yeah, good point. The number of models that we need to fit in here is again 1 plus p minus 1, p minus 2, p minus 3, all the way to 1. So again, the number of models also for backward stepwise is this. Again, we have p to the power of 2. So in comparison with best subset, this is more computationally efficient. But if you want to compare it to forward stepwise selection, actually this is not as good as forward stepwise selection. I mean, depending on the situation. The thing is with forward stepwise selection, which is this one, we can start from here and move forward and stop wherever we want. So if p is large, then the x-axis of this is going to be really long. So with forward stepwise selection, this is feasible. These are feasible, and we can just continue this up to some point and just decide to stop here. Maybe when we get to, let's say, 4 predictors out of 500, we can just stop here and say this is good enough, right? But with backward stepwise selection, as we need to start from 500, as we need to start from the right, the first model that we want to fit is going to be difficult, especially in the case where p is larger than n. This first model cannot be fit using ordinary least squares. So in that sense, for cases where p is larger than n, forward stepwise selection has an advantage over backward stepwise selection, because it starts with something simple and just builds on top of it. So we can just stop the process wherever the fit is good enough. But with backward stepwise selection, we start with the most complicated model, with the most dense model, and then sparsify it step by step. And in this situation, we cannot even start this with ordinary least squares.
So my question would be, as you mentioned previously, the collinearity may exist in the forward method. But either with backward, that will kind of eliminate that issue since we have content all features at the beginning. So either backward is better in this case.
No, actually, also for backward stepwise, this is the same thing. So if this is 0 and 0, if best subset takes us here, eventually with all p predictors, so this is 1, r squared, also backward is going to be just some local optimization. This is because here, we remove a feature. When we remove it, there's no way to bring it back later in the model. So maybe this feature is gone here, but it becomes something informative further down the line. But with backward stepwise selection, there's no way to give that feature a chance to reappear in the model, because our search is kind of in a greedy way and in a local way. And when we get rid of something, we never let it come back to the model.
I'm just saying with backward compared with forward.
They are pretty much the same. And just theoretically, when we have forward stepwise selection, we can also implement the same idea in the backward way. But because of this, forward stepwise selection is a normal thing to implement. Any other questions? All right, let's take another quick break, and then we're going to talk about regularized fitting.